Hello everyone. Today I'll be presenting on the topic instruction set of a basic computer. So before we get into defining what an instruction set is and what a basic computer means, we should be clear about what we want to achieve. And I'll start by taking an example. So you all write a C or C++ program in your IDEs, right? Okay. So all those C and C++ programs have some variables and you do some operations on those variables. Now, what does it mean for the internal organization of your computer? You have written a high-level language, you have written a code in a high-level language. The computer won't understand it, so the compiler converts this into a lower-level language that it can understand in form of zeros and ones. And in the way we interpret zeros and ones is by associating some codes to it, and that is what we call assembly language. All these instructions are basically just the binary format that's designed and predetermined by the designer of the computer. Now, let's assume that a program in a given high-level language and the compiler it is associated with, the compiler converts it into a set of instructions that's stored in the memory that uh, that gets stored in the memory. So we have these instructions here, instruction 1, instruction 2, instruction 3 that's stored in the memory. So how does the basic architecture of the computer would execute these? So that is what we want to achieve. And these are the 4 steps that we can use, that we'll have to use to get that. So the first one is to fetch the instruction from memory. Here's the memory, and there are instructions in the memory as placed by the compiler with the addressing modes and the rules that the compiler follows. The first step is to fetch that instruction from the memory to the processor that we are using to execute the program. The second is once we got the instruction, we'll get an instruction in the form of a stream of bytes, in a stream of bits. So there'll be particular sections to what those bits mean, and that is what is called an instruction to as it is defined for a particular processor. So particular sections of the instruction would mean different things for different instructions. And in the basic computer, we follow one such rule that it it has a 16-bit instruction. Out of those 16-bit, the most significant bit denotes the addressing mode. Is it a direct addressing mode or indirect addressing mode? And the next 3 bits, they determine the opcode uh, of the instruction, as in what instruction or what action does the instruction have to actually perform. And the rest part from bit 11 to 0 depend on what type of instruction we have. And and the third step is if it is an indirect addressing mode, we have to get the effective address of the operand from the memory. The effective address is where our actual operand is stored. And the fourth step is to execute the instruction and repeat the process until we get a halt. Okay. So this is the basic architecture of a basic computer, the processor registers and the memory unit. The memory unit is not a part of the processing of the processor registers. AR denotes the processor register that stores the address. PC is the register, a 12-bit processor register that stores the address of the next instruction. DR is data register. It stores data from either memory or AC or whatever the use case may be. AC is the accumulator register, and it's the most useful register in this architecture. Every operation that happens inside or within the AC or it's indirectly or indirectly associated with the AC, especially the arithmetic and logic actions. IR is the register that stores our actual instruction that's fetched from the memory. CR is a temporary register that can be used for various purposes temporarily. And INPR and OUTR are input registers and output registers that are used to fetch and send input and output respectively to the peripheral devices. Now, this is the basic instruction set that I had discussed in the previous slide. This is the indexing mode, the addressing mode, opcode, and this may be either address or something else. And it depends on what type of instruction there is. So we have three types of instructions for a basic computer. The first one, memory address. The second is register address, and the third one is input output instruction. Memory address instructions deal with operations on the memory unit and AC. Register reference instructions uh, deal with operations on AC itself. Like, do you want to clear AC or do you want to branch somewhere else? So register reference instructions, they deal with all these processor registers. And input output instruction, they deal with the input and output, the setting or deploying the output, setting of the input or deploying the output. Now, to achieve this in reality, we develop a flow for the die, a flow for the entire process. And to execute that flow, to make it real, we have something called control signals. Now, what are control signals, and how is this opcode actually used to bring about the changes that we need the computer to do? So we use a sequence counter and the opcode, and based on the values of these two attributes, we set our load, increment, and clear inputs of these registers. It will make more sense when I'll discuss a slight peek of the control logic gates and the entire instruction set. So what happens is a 4-bit sequence counter is used, and as and when the sequence counter is triggered by the clock, at each tick, the values that come out of the decoder will change. So at any moment, there's only one output signal for the 4x16 decoder that would be enabled. So at any moment, only one of T0 to T15 would be enabled. And similarly, we have a decoder for the opcode as well. As the opcode is 3 bits long, we can have 8 distinct states for the opcode. Now let's Now let's focus on the instruction set itself, like and how these instruction sets are divided into three categories. So for that we use opcode field. If opcode is 111, we can have either register reference or input output instruction. And if it is any other value than 111, then it is a memory reference instruction. And if it is a memory reference instruction, we use the this most significant bit to determine the addressing mode of that memory reference instruction. If the addressing mode is set to 1, if the most significant bit of this instruction set is set to 1, the addressing mode is indirect, and if not, it is direct addressing mode. So moving on, this is the basic flow of what will happen or what should happen in during one cycle or when one instruction set is executed. So we start with setting our sequence counter to 0. That will set our T0 variable. Now this is interrupt is set to zero because we are not touching the interrupt cycle right now. R is also a variable that's used to differentiate between whether an instruction cycle should be executed or the interrupt cycle should be executed. So we'll first move to the instruction cycle. Let's assume the instruction cycle is fetched. For that, we need to fetch the instruction, the address of the instruction and place it into AR, that's the address register. We read the value at the address stored in AR into IR, that's the instruction register, and we increment PC, that's program counter, to by 1. Now, now that we've got our our instruction set at time t2, we decode the value of bits 12 to 14, as I explained here, bits 12 to 14 into D0 to D7 variables, and we set our I flip-flop according to the value of the most significant bit of the instruction set. The rest is stored in AR. Now we inspect D7. Why D7? Because if it is triple one, D7 would be set. And if D7 is 1, it means it's triple one, and hence it would be either a register reference or an input output instruction. And if D7 is 0, it means the opcode is anywhere between 0 and 6. That means the instruction is a memory reference instruction. Next, we inspect the I flip-flop that we have set according to the value of the most significant bit of the instruction set. For D7 equals 0, that's memory reference instruction, we just inspect the value for getting is it an indirect addressing mode or the direct addressing mode. In indirect addressing mode, the let's say you get 500 as the value in the address field, and the addressing mode is indirect 1. So at 500, let's say 103 is stored. So what this means is at location 103, whatever value is stored, that will be our operand. So we fetch 103 into AR again, and then we set to execute our memory reference instruction. And if it's direct addressing mode, we set the T3 down, and then in the next clock tick, we execute it directly with value 103. Yeah. So memory reference instruction, this is the addressing. This is what the instruction would look like. It would be either 1 or 0, the most significant bit, and opcode would be anywhere between 0 to 6 and 8 to E. It means it could be 0 or 1, the most significant bit out of 4. And the next 3 would be from 000 to 111. This could be 0. From 000 to 110. So it's 0, 110, and it's 1110. Yeah. For register reference instruction, the opcode bit would be 111. It means D7 is active, and the most significant bit would be 0. So these are the hex values of the entire instruction set, and these values, now for the address field of this instruction, it doesn't give any particular number of numerical significance. It gives a stream of bits in which only one bit is set and the rest are 0. So whatever bit is set, that determines we determine it by B subscript I, and that determines what should happen next. So if the first of the 12 bits of the address field is set, we clear our AC register. If the second bit is set and the rest are zero, we clear the E flip-flop. And likewise, we have these many instructions in the register reference instruction mode. For input output, the output value is 111 and the most significant bit is 1. So when we want to gauge what way our flow should go, we are basically coming here. D7 is 1 because it's 111, the opcode, and since the I bit is set, the most significant bit, it executes the input output instruction at T3. This is also a control variable, and we'll make use of it in the last slide. So yeah, and according to the value that it gives, this is also the same for from the stream of bits of 12 bits, only one of those bits is set, and according to that set bit, in the last field of the instruction input output instruction, we determine what action should take place. Now this seems like an abstract command, but this is achieved by a set of micro operations, as we'll see later. So coming back to the top, we'll start from the fetch and decode phases. If at T0 we'll fetch the instructions, uh, at T0 we'll fetch the instructions address, and then we'll resolve that instruction from the memory and store it into IR. And all of these micro operations they take place. As I said, these might seem abstract, but there's a series of micro operations that's running behind them, behind the scenes. And likewise, we get these control variables and they are associated and they're corresponding in micro operations. Now, on the basis of this, we have this architecture, right? Everything that we need to do needs to be done in this architecture. So how do we achieve it? For every processor register, we have three inputs that determine what the state of a register should be. If the load input is enabled, uh, it suggests that the value from the bus should be stored in the register. If the increment label input is set, then it suggests that the register should increment itself by 1. If the clear input is set, then the register should be clear to 0. So we use these inputs to bring about changes that we need. And for that, will take an example for changing AR. Let's say I want to set AR. So this defines the entire instruction set and the code of what our computer would execute given the conditions. So for example, if I want to see where my AR changes, so I'll search for all those macro operations in here that give that has this format: AR and the back arrow and something. So I'll search all those instructions and I'll mark their control signals. So one I can see is uh, R naught and T0. Another is here D7 naught I T3, and here it's clearing it basically. So we'll put it in the clear register and AR. And R not T2. So these three are being used are the states when AR changes. As you can see, AR changes when it's set by PC or IR, the last 12 bits of the instruction set. And these are the control inputs of what they should be like, what these variables should be when AR changes. So we see that for these three commands, for these three microoperations, AR is loaded some value. So we give the control input or them and give it to the load input of AR. So whenever one of these is true, we know that the bus AR should load the value into it from the bus. So from the bus, whatever value is coming, if these any of these three control inputs are set, then the load input will be set to 1 and the data from the bus will be copied to AR. Likewise, when AR is set to 0, it means it's cleared. So we need to enable the clear input. And when that should happen, when R and T not are true. So when R and T not are true, this is for R and this is for T naught. So it's simple AND gate. So when R and T naught are true, we set our clear input. When clear input is enabled, AR will be set to 0 as it should happen from the series or from this list of instructions that we've made. And likewise for interrupt signal, we have D5 T4. So this is what happens behind the scenes in the control gate portion of our microprocessor right here. All these gates that I've explained, they are stored in the gate section of control gate section of the microprocessor. Where is that? Yeah. Likewise, we'll have load inputs and increment inputs for all of these registers, and all those gates are distinguished in this section of the microprocessor. So this is how an instruction is fetched, it's decoded, and its effective value is calculated, and the instruction is executed on the basis of this flowchart. And the control gates is how we bring about the change and how we carry out this flow of the instruction fetch and decode cycle. So that was all for today. Thank you.